Okay, my dear friends, hoping that you are all fine with the blessings of Almighty Allah. And right now we are solving paper 6, variant 3, and this is year October-November 2020. So paper 6, variant 3, October-November 2020, and let's start it. So we are starting with question number 1, which is based on some thermal physics question. Some students investigate the transfer of thermal energy from a beaker of hot water. They use the operators shown in figure. Now you can see there are two beakers. One is A, other one is beaker B. One beaker A, it is without lid, and beaker B is with lid, and a narrow opening is there so that at the surface of this one, so that the thermometer can be placed through this lid into the hot water. A diagram shows the thermometer. Figure 1.2 shows the reading on the thermometer at the start of the investigation. And what we are supposed to do, record the room temperature theta R shown on the thermometer in figure 1.2. So see how much is this. We need to beep it. Now see if we are reading it, because we are covering it. So yes, see, this is 20. So this is 24, 25, 26, 27, 28, 29, 30. So we can say the temperature here is 24, and don't forget to write the unit, which is degree Celsius. So that is the reading, or that is the temperature of the room, or we can say simply the room temperature. Okay, and even it will be recommended if you can write 24.0 degrees Celsius. That will also be workable. Okay, next is, my dear friends, a student pours 100 centimeter cube of hot water into beaker A. He records the temperature of water in beaker A and immediately starts a stop clock. He records the temperature of the water in beaker A and immediately starts a stop clock. So the student records the temperature theta of the water every 30 seconds, means on interval of every 30 seconds. His readings are shown in table 1.1. The student repeats the procedure for beaker B. Beaker B is fitted with a lid. Complete the column headings and the time column in table 1.1. Time, it is already mentioned in seconds, so we will say time is in seconds. Temperature is in degrees Celsius. In both the beakers, temperature is measured in degrees Celsius. And then also column for time we have to complete every 30 seconds. So 0 plus 30 is equal to 30, 30 plus 30, it is equal to 60, 60 plus 30, 90, 90 plus 30, 120, then 120 plus 30, it is 150, and then 150 plus 30, 180, and all these time intervals are in seconds. Describe a precaution that should be taken to ensure that the temperature readings are as accurate as possible in this experiment. So temperature readings, it means we should more likely to think about the temperature reading from thermometer. So we can say simply line of sight is at 90 degree to the scale of the thermometer. So line of sight is at, or keep line of sight, even you can add one thing, that keep line of sight at 90 degree to the scale of the thermometer, then we don't need this is. Anyhow, now I made a bit change in the statement, so there is a bit gap, don't worry about this. Then write a conclusion stating how using the lid affects the cooling of water. Using lid affects the cooling of water. So we can observe one thing. See how much temperature fall is there. 85 minus 50. If I'm checking here change in temperature or fall in temperature, see in 180 seconds 85 minus 56.5. What is the difference, my dear friends? Our fall in temperature, this is 85 minus 56.5 and answer is 28.5 degrees Celsius. It means 28.5 degrees Celsius temperature is fallen. What about when there is a lid? So you can check here 86 minus 76, that is equal to 10 degrees Celsius only. What does this show? That rate of cooling decreases when the lid is placed on the beaker. So what can we write here? We can write write a conclusion stating how using the lid affects the cooling of water. Okay, which beaker is using the lid? Beaker B is using the lid. So we can say temperature falls more slowly in beaker B. The temperature of water in each beaker decreases during this investigation. Describe one other similarity in the pattern of cooling of water in beaker A and B. One more pattern is there, and that is a bit tricky question now here. See, in the first, let me say in the first 90 seconds, temperature fall here is almost 17.5, and then in the next 90 seconds, it is only 12. I'm sure you are getting me. I mean, up to here temperature difference is more, temperature fall is more in the first 90 seconds as compared to in the last 90 seconds in this case. And also here see 86 minus 78.5, so it means almost 7.5 degrees Celsius is fallen, and then only 2.5 degrees Celsius in the next 90 seconds. So what is happening? The decrease in temperature decreases with time. Or I can write cooling, rate of cooling we can say, because we are relating it with time. Rate of cooling decreases as the temperature falls. As the temperature falls. So only one mark, this is more than enough, that in the beginning temperature is falling more quickly, and then later as the temperature is decreasing, so the rate of cooling is also decreasing, and that you can observe in the first 90 seconds for beaker A, in the first 90 seconds for beaker A B, and then in the last 90 seconds for both of the beakers. We will say for beaker A in the beginning, early 90 seconds when the temperature is much higher than the room temperature, so rate of cooling is more, and in the last 90 seconds rate of cooling is less. You can make the difference between the numerical values as I did before while explanations. Now next is calculate the average rate of cooling XA of the water in beaker A. Use the values of theta A from the table 1.1 and the equation XA is equal to theta 0 minus theta 180 over T, and T is of course equal to 180 seconds. But question is, what is theta 0? It is the temperature at T is equal to 0 degree, mean the initial temperature, or you can say the starting temperature, and theta 180 is actually the temperature at time 180 seconds. So include a unit also. So what we can write, XA is equal to theta 0 and 180. Come here, theta 0 is 85 and 180 is 56.5. 85 minus 56.5 over 180 seconds, because include unit, so better write the unit with numerical values. So 85 minus 56.5 over 180. Let's see. 85 minus 56.5 equal to 28.5 divided by 180. So answer is 0.1583. So answer is 0.158. So I can round it off to 0.16 degrees Celsius per second. Then my dear friends, the same thing we have to check for beaker B. Same scenario. Now XB will be equal to, let's check what, see, initial value is 86 and final value after 180 seconds it is 76. So my dear friends, 86 minus 76 over 180 seconds, and here you should write degree Celsius as we are simplifying. So it is 86 minus 76 equal to 10 divided by 180. Answer is 0.0555. So 0.0.0.0 0.0555. So what I'm going to do, I'm going to write 0.056, and don't forget to write the unit degree Celsius per second. Yes, my dear friends, if there is any question, any ambiguity, any doubt, feel free. Even you can write later in the chat box on the YouTube channel. Now, the thermal energy is transferred from the surface of the water and from the sides of the beaker during the investigation. So students suggest that more thermal energy is transferred from the surface of the water than from the sides of the beaker. So state whether your results support this suggestion. Justify your statement by reference to the values of XA, the average rate of cooling without a lid, and XB, the average rate of cooling with a lid. So statement is yes. Why? When there was no lid, rate of cooling was much more. It was 0.16 degrees Celsius per second. But when there was a lid, so rate of cooling is 0.056 degrees Celsius per second. So this is less than half even this rate of cooling of XB. So we will say yes. As I told you, you can say that XB is smaller than even half of XA. Why we are saying this less than half of XA? Because if it is half of, so that they said more rate of cooling is faster when there is no lid. In other words, the lid is stopping a lot of heat to escape from the surface of the liquid. So if there will be no lid, it means the heat will be lost to the surroundings more quickly, not only by evaporation but also by convection. And there should be big difference if we are comparing the heat losses from the surface and from the sides. And they said here, students suggest that more thermal energy, so it is transferred from the surface of the water than from the sides. To prove that this is more thermal energy is lost, so the energy lost by without lid, it should be more than half of that which is lost from the sides. So that's why I have written it this way, that XB is less than half of XA even. So more heat is lost by the surface of the water. XA is the beaker, is the rate of cooling for the water in a beaker without the lid. Then, my dear friends, suggest a change to the apparatus or the procedure to produce a greater difference between XA and XB. You can say make higher initial temperature. Make higher initial temperature, so it will make a even greater distance. So increase the initial temperature. Higher initial temperature of water will produce a greater difference between what? Between XA and XB, which are the rates of cooling of water into different beakers, one with lid and other one is without lid. Okay, my dear friends, let's move forward now. And next question is on electricity. Some students investigates an electrical circuit containing different combination of resistors. They use circuit A shown in figure 2.1. Circuit A is not shown complete. Of course, there are some parameters missing. On figure 2.1, complete circuit A to show a voltmeter connected to measure the potential difference across the resistor X. An ammeter connected to measure the current in the circuit. My dear friends, ammeter is always connected in series in the circuit to measure the current, and voltmeter is always connected across the component where we need to know the potential difference. So it means voltmeter we can connect here this way and just simply join this line. You will score 2 marks. And again I'm repeating, voltmeter we are not connecting only in parallel. It is connected in parallel or across the component where we need potential difference. Right now we need the potential difference to be measured across X. So that's why voltmeter is connected across X. An ammeter to know the current in the circuit. So it means ammeter should be connected in series in the circuit. So that's what I have done. I have connected it in series in the circuit. And the other gap here I have filled it with a wire, or that is circuit is completed. An ammeter, it is not necessary that it should be only on the right hand side gap. Even it can be on the left hand side gap, because both of these gaps are connected are made in series with the whole circuit. Then a student measures the potential difference V across X and the current in the circuit. The voltmeter reading is shown in figure 2.2 and ammeter reading is shown in figure 2.3. Record in the first line of the table 2.1. Of course, that table will be on the next page. The values of V and I shown on the meters in figure 2.2 and figure 2.3. So first of all, voltmeter values. So see, if I'm going for one small division, that is 1 minus 0 divided by 10. So from 0 to 1, okay. So it means each line is representing 0.1 volt. So 3, 3.1, 3.2, 3.3. So ammeter reading is basically voltmeter reading is 3.3 volts. Now what about the ammeter reading? Ammeter reading, we can check that one small division is equal to, again see, 0.2 minus 0 over 10. So it means 0.02 amperes. See, from this value I have checked. Now see 0.6, 0.62, 0.64, 0.66, 0.68, it means this is 0.7. Then this is 0.8 and the next line will be 0.82. So current here is 0.82 amperes. So let's add these values to the circuit or to the table. So voltage is 3.2, 3.3 here, 3.3 and current is 0.82. Now next is the student now connects two 5 ohm resistors in series between P and Q as shown in figure 2.4 to form circuit B. The rest of the circuit remains as in figure 2.1. So X is replaced by another 5 ohm resistors. She measures the potential difference V across the resistor X and current I in the circuit. So X is not replaced, but two resistors are connected in series now. So these values are, the student then connects three 5 ohm resistors in series between P and Q as shown in figure 2.5 to form the circuit C. The rest of the circuit remains the same. She measures the potential difference PD, potential difference V across the resistor X and current in the circuit. All her readings are shown in table 2.1. Complete the headings in the table 2.1, but before solving this, see here between P and Q only one resistor. Then after collecting the data for V and I, what the student has done, the student has connected another 5 ohm resistor between P and Q in series with the previous one, and again read the values of current from emitter and the current of potential difference across X by voltmeter. And then the student repeated by connecting three 5 ohm resistors between P and Q and rest of the circuit, and scenario is same. Now first of all we are told to complete the column headings or headings in the table 2.1. V capital for volts, current is ampere. So the headings are completed. Then calculate and record in table 2.1 a value for the resistance R of the X for each combination of resistor the student has used. Use the readings from table 2.1 and then equation R is equal to V over I. So 3.3 over 0.82, 3.3 over 0.82 3.3 divided by 0.82, we are getting 4.02. Okay, 4.02. Then 2.1 divided by 0.54, 3.88. So we can say it 3.89, and then in the end 1.6 divided by 0.39, 4.10. These are the three values. Now after doing so, now here's formula question. A student suggests that the values of R should be the same. State whether your results support this suggestion. Justify your statement by reference to the values from your results. So what we are going to do, first we will calculate percentage error. If it will be less than 10%, okay. If it will be more than 10%, then it is not okay, it will be no. So what I'm going to do, see 4.02 and 4.10, they are very near. I'm finding 3.89 and 4.10 percentage error. And what is the method which I have told you many times already? So we are going to calculate now percentage error or uncertainty 2 times 4.10 minus 3.89 over 4.10 plus 3.89 times 100%. So when I am calculating these values, so first of all I want to do 4.10 plus 3.89, it is 7.99. okay, I was willing to get this value. Now 7.99, but see, we will do 4.10 minus 3.89 equal to 0.21 divided by 7.99 equal to this, then times 100 equal to 2.62 times 2 Answer is 5.25. So 5.3% almost. This is less than 10%. See, I have not taken the nearest values, I have taken the values which are with the maximum difference. One is 3.89, other is 4.10. Now percentage error is 5.3%. So they said the values should be same. Yes, they are same because not a big difference. Yes, and then here you can use the formula statement that within the limit of experimental accuracy. See, if the error is 5.3%, it means accuracy is 94.7%, high rate of accuracy. So that's why they are almost equal. The results can be checked by using different circuits. Draw on figure 2.6 one other arrangement of three 5 ohm resistors between terminal P and Q. So what other between P and Q, what can be the other so what I'm going to do, another thing I can do here, see, one 5 ohm resistor, then I can connect other combination. So this is like this. So one is series, other two resistors are in parallel. So these are different combinations of resistors. Then a student wants to determine R by using a variable resistor to vary the current in the circuit. Now draw the circuit symbol for a variable resistor. This is a very common question. So variable resistor, arrowhead like this. Explain one advantage of using a variable resistor to vary the current compared to the procedure carried out in B and C. So here we can say student can get more values easily. There is no need to connect and disconnect again and again to get the new value. So easily the student or the experimenter can get more values for current, more values for resistance, better to say more values of current easily, more values of current. Let me write that is better, more values of current easily. Okay, my dear friends, stay blessed. Thank you.